Namaskar. Welcome to this particular course. No need to welcome you to the Indian Institute of Science because you've been here for at least a semester, most of you. Anybody who is not a first year MTech student in this class? Yeah. What degrees are you registered for? Okay. Both of you? Yeah. Anybody else? That's it? Only two? Okay. Which years are you? Good. Okay. So IISc is not new to you. But within IISc, I would like to welcome you in particular to my lab in the Department of Aerospace Engineering, which we call as the NMCAD lab. The reason why I have a couple of slides about our lab and about the gentleman here in the front row here is that you'll be interacting with them quite a bit over the semester. And so it's good for you to know where we come from in terms of at least our professional and academic backgrounds. Keeping that in mind, I would take a few minutes to describe the lab that I had in the aerospace department so that you are aware of the kind of research that we do. Some of the things that I might state as part of the flight mechanics course come from my own understanding of aerospace from that perspective. So there will be a tinge of probably, if you call it prejudice or whatever, but I'll try to see, as I mentioned in the introductory email that most of you might have read, to make it as holistic as possible so that the shades of me being a structures and materials person, so to speak, do not appear through this particular course. Okay. There are reasons why it would not. I would shortly explain to you the acronym, what each letter stands for. But before that, very interestingly, and to the liking of many of my current students and alumni, we call ourselves NM cadets, and I happen to be one of them. My name is Dinesh Kumar Harur Sampath. I've done my PhD at Georgia Tech in Aerospace Engineering. This is my email address, and of course, all of you are part of the teams. That team is essentially for us to communicate because all the classes will be in person, Mondays and Wednesdays, 2 p.m., same time. Forgive me for keeping it immediately after lunch. I know many of you will feel sleepy, but I'll try to make it as interesting as possible that at least out of the 2 hours, you listen in at least for an hour. And that will be good enough in terms of takeaways. This is, as you know, 201A. That's the very first course in your, if you look at the scheme of instructions, there's no number which is earlier than this, at least so far, because we are soon going to have an undergraduate program in aerospace engineering from the coming semester. Not the summer, but the fall, which means we'll have some 100 level courses as well. So, but nonetheless, this is the lowest number that you get. So in some sense, it's a minimization problem that you're looking at. Another peculiar thing about this is most of your courses have been 3 credit courses and will probably be. A few maybe 1 credit as well. But this is a 4 credit course. And this is after a lot of arguments and a lot of debates in the faculty meetings. When I was teaching this, I was teaching it as a 2-part course. The first part where we look at essentially aircraft performance and also orbital mechanics. The second part where we look at the stability and control, what we call as atmospheric flight dynamics, the name of the course. 2 3-credit courses was a little difficult, but 1 3-credit course as a core was not sufficient for such a vast topic. So which means that we were arguing for a 4-credit course, and that's why it is 4. Which is also a reason why I have it after lunch so that I can get 2 slots adjacent to each other, the 2 to 3 Monday, Wednesday, Friday slots and the 3 to 4. Except that, of course, you have a long weekend from my side. In terms of Fridays, we don't have a class, so we have only on Mondays and Wednesdays. Strictly speaking, anything related to flying in space also is flight in a sense. It's just that it's not atmospheric flight, but you're flying in deep space, which means a rarefied atmosphere. Very little is there, if not vacuum itself. But nonetheless, to stress the fact that you're all aerospace engineers. For a long period of time, departments like ours, worldwide, including in the IITs in India, have been called aeronautical engineering. And sometime in the 70s, 80s, at different locations, they changed over to aerospace engineering because they wanted to cover a bit of the space studies as well, which is what we will try to get a flavor of in 1/3 of this course. So even though it's a 4-credit course, we'll kind of divide it into 3 parts, 1/3 each, where the first third will be related to aircraft performance. And when we talk of aircraft, we will restrict ourselves to fixed wing aircraft, though there are many others like helicopters and flapping wing, drones of interest lately, etc. But we will stick to that. And in space mechanics, we'll primarily be looking at orbital mechanics, what historically we have learned from the movement of planets around the sun, and how we have translated that to understanding the orbital trajectories of satellites, and also the launch vehicles which need to take them there. So launch vehicle is kind of a connection between the two, because remember, it starts from the Earth's surface and then you're launching a satellite. So initially it flies through the atmosphere, and then it depending on what kind of payload it's carrying, it might enter into the space, what we typically define as the von Karman boundary, which is essentially about 100 kilometers for all of us to understand. There's nothing significant which happens specifically at that boundary. It's more of a thumb rule in terms of what you consider as atmospheric flight and space flight, right? In fact, when astronauts go, they cross that 100 kilometers. For example, if you're going to the International Space Station, if there are newbies on board, they are welcomed to the space for the first time by the rest of the crew, just because you've crossed the 100-kilometer mark. Of course, as some of you might know, the International Space Station itself is at about 400 kilometers. But when you're talking of these numbers, they might sound by themselves very big. But when you're traveling on the ground, you know that 400 kilometers is just nothing. A little more than the distance from here to Mangalore or here to Chennai, for example, right? Or to Hyderabad. So that's essentially the kind of distances that we're talking about. So in terms of the vastness of the Earth, if you're looking at, it's not a perfect sphere, but it's oblate. But on an average, you have a radius of about 6,400 kilometers. And here you're talking about even 400 kilometers as the space line is a fairly small fraction of that 6,400. So in a sense, you're still bound by the Earth. And in terms of the distances from the other so-called planetary bodies, in which we also include the moon because it's a massive object, though it's a natural satellite of the Earth. But you're talking of the distances, then you're obviously talking of much, much larger distances there, about 400,000 kilometers instead of the 400 kilometers that you're talking about here, right? So when you're talking about things like that, or 40,000 kilometers, so if you stack up, let's say, 108 moons, you essentially get to the Earth, or 108 Earths, you stack up, you get to the Sun. So the significance of this particular number, 108 in a particular sense, when you're talking about the actual cosmic distances that are involved. And there's a lot of parallels in terms of how these orbits happen, let's say in an atomic scale, where the electrons going around the nucleus containing the protons and the neutrons, and then what you're talking about in terms of the planetary orbit. So at very small length scales and very large length scales, which are typically governed by very, very different kinds of physics. When we go to very small length scales, we call it quantum or quantum mechanics. And when we are talking of larger scales, you're talking of continuum mechanics, especially if the densities are reasonable in terms of the distances between particles related to the size of the particles, average sizes. If it's not if it's of the same order, then you can typically deal with it as continuum instead of a rarefied particle mechanics kind of an approach. So Keeping that aside, now we come back because in the first 2/3 of the course, we will not even get there to orbital mechanics. We'll be talking about, I might jumble up maybe if you're getting bored with flight mechanics too much, maybe I'll put the second half, which is stability and control, after orbital mechanics and sandwich this. So we'll take a call on that when we finish the first third here in terms of the aircraft performance. But nonetheless, what I'm saying is that when you're talking of atmospheric flight dynamics, just for the purpose of communication between, let's say, teacher and student, and more importantly, between people who are operating flights or designing vehicles, etc., for these purposes, you will see that there's a common language that we need to speak. Otherwise, it could be disastrous. You have heard examples perhaps of people mixing up units between FPS and SI system, and that creating huge issues. So units is just one aspect of it. Other is also in terms of an understanding of how our atmosphere actually behaves, because it's a very, very complicated animal. In fact, a butt of most jokes is the weatherman in terms of the prediction of the weather, in terms of what kind of conditions you might have even on the surface of the Earth, leave alone at higher altitudes. Even though von Karman line is about 100 kilometers, most of the aircraft that we will be talking about in 2/3 of this course will be things which will be flying perhaps around 12 kilometers altitude, which is very, very small. If you're looking at 6,400 kilometer radius or 12,800 kilometers in terms of the diameter, or if you're looking at the circumference going around the Earth, about 40,000 kilometers. So compared to that, 400 is just one person. So you're really talking about very, very small numbers. And here you're talking of 12 kilometers, which is an even smaller fraction. Now coming to the Earth itself, you know that we complain about potholes and things on the road, very bumpy ride and things like that. But the highest level that we go away from the surface of the Earth, which we typically define as a mean sea level, is Mount Everest. And how tall is it? Yeah, so about 8.8 kilometers. Now, 8.8 kilometers divided by 6,400 kilometers radius, such a small percentage. And but by the time you go to the top of Mount Everest, you're panting if you're not trained enough for it, or even if you're well trained for it. A lot of mountaineers find it very difficult, because can you approximate what kind of pressure you would have there compared to 1 atmosphere here? What would be the pressure on top of Mount Everest? Approximately. Would it reduce or increase? Reduce. That everybody agrees. So how much would it reduce by? Just to get an idea, because it's very important for us to understand these numbers, get a feel for it. Okay. Once you get a feel for these things, then when you look at the theory, the equations, etc., they become much more of speaking the same language which you already intuitively understand. Otherwise, it gets too boring. So which is why. So any takes approximately? 0.5 is a good approximation, but it's even lesser, about 1/3. Okay, so 1/3 is what you have, and which is why the oxygen content is also obviously reduced by 1/3, and therefore a lot of people find breathing issues. It becomes very difficult. They can't stay for much longer, and it doesn't support life, which says a lot in terms of the amount of oxygen that is available there, in spite of all the ice, which is essentially water in a solidified form. So we are talking of, in spite of looking at this from a perspective, when you're looking at yourself on the ground, 8.8 kilometers looks really awesome, magnificent. If any of you have been to other parts of the Himalayas, you know, even smaller peaks, they look so magnificent, and it's so amazing, such an amazing sight. And then when you're talking about aerospace engineering, you're going much, much beyond that. So all these things about Copernicus, Galileo, etc., over a long period of time, trying to move from a flat Earth model to a round Earth model, which of course was there in a lot of our scriptures in terms of calling it goal already. But from an understanding of actually looking at it from an experimental perspective, actually visualizing that, only when you go far enough, you get that view of looking at what it is. And geostationary satellites are a great example of that, which have a period of 24 hours around the Earth, which is also the period, as you know, of the Earth rotating on its own axis, which, by the way, is tilted. And that tilt in the axis is what causes precession, and therefore a difference between what is known as a sidereal zodiac, which we follow typically in India, and tropical zodiac, which system which many of the Westerners follow, both in science as well as astrology for that matter. So when you're talking of astronomy and astrology, etc., it's very important to understand various aspects of these in a much more finer perspective. And that's when you try to include various types of motion, etc., into the whole perspective. And when you do that, you see that some of the effects sometimes might be negligible, and that's when you can safely neglect them from an engineering point of view. But from a scientific point of view, it should be something that you test and then leave out, rather than assume that it is not going to make much of an effect. So that's as far as the distinctions between flight and space mechanics is concerned in terms of an overall qualitative perspective. And as I said, here we'll be talking of initially performance. So all said and done, whether it's an aircraft or a spacecraft, it's a vehicle. It takes you from point A to point B, and hopefully for space vehicles, it brings you back as well, point B to point A. So what we talk of re-entry, and we'll talk about the complications involved with the re-entry vehicles, etc. But when we're talking of the first third of the course, we'll be talking about the performance of the vehicle. We would like to know what is the typical performance parameters we look at. And they're not very different from any of you going to buy a two-wheeler or a four-wheeler, let's say. What are the things that you typically look for when you're buying a new vehicle for yourself on a road vehicle? Mileage, yeah. So that's a typical Indian way of looking at it right up front, and which is also what we say, what was called as, I don't remember the exact wordings, but paraphrasing it. So essentially, it's cheaper than an auto ride in terms of per kilometer going to the Mars in Mangalyaan. So something like that. Yes, mileage is very, very important. You have a corresponding thing in aerospace as well. Some of you, all of you have, in fact, except the undergrads, have taken the course on mechanics and thermodynamics of propulsion. So what is the equivalent of mileage over there in talking? Yeah, SFC, or specific fuel consumption, is what you're talking about. And then when you're getting into, let's say, rocket engines, you'll see specific impulse, etc. Right? Now coming to so that's one performance you look at when you're buying a vehicle. Anything else for a road vehicle? Speed, yeah. So when we're talking of speed in the case of an aircraft, you're talking of multiple speeds over here. In fact, on a road vehicle also, you talk of multiple speeds. For example, what is the maximum speed that your vehicle can go? The other is, of course, what speeds or range of speeds at which you get the maximum mileage, going back to the first question over there, right? So also in terms of the ability to climb steep paths, what is known as a pickup in a colloquial term is essentially the acceleration, 0 to 100 kilometers per hour in a certain number of seconds, or whatever the measure is for a typical kind of vehicle class that you're talking about, right? So what else apart from speed? So here you're talking of, in the case of the aircraft also, the equivalent of the maximum speed you have here as well. In fact, here you have, for cruising, you even have a minimum speed. What is that typically dictated by? Yeah. So some of you know that because based on your aerodynamics course or fluid dynamics course for that matter. So essentially that's, for those of you who don't understand, don't bother. We will talk about all these terms. So if you don't understand any of these terms that some of the students are replying, we will cover those in a way that a typical high school student can also understand. So don't worry about things that you don't understand, right? So apart from a maximum speed, there is a minimum speed, right? And then unlike a motorbike or a car, which especially in Bangalore, you can park anywhere you like. And that's something that some of my colleagues keep complaining about, seeing motorbikes and cars parked in places where they're not supposed to. Leaving that aside, there's much more stricter rules when you come to aircraft, right? Because they need airports. Because we are talking about fixed wing aircraft, remember? Not talking of helicopters which can land in helipads or some even more non-conventional or surfaces which are not specifically designed for that, especially when you're looking at military helicopters, etc. Right? Now, coming back to this, here you need an airport, you need a runway, you need an airstrip which of a minimum length depending upon the class of the aircraft, because you need to achieve a particular speed before you can take off. Otherwise, you're not going to generate the lift that you want. So that's another speed that you're talking about. Then again, in terms of here, you're not talking of a two-dimensional motion. All said and done, in spite of your ability to go climb mountains, etc., with your two-wheelers and four-wheelers, we are on the surface of the Earth. Okay, yes, it's not a flat surface, but it's a curved surface. At the end of the day, it's a two-dimensional surface, because surface by definition is two-dimensional, on which you're riding, which means that they're only from a positional point of view, translational point of view, there are only 2 degrees of freedom, right? Which is X and Y, right? Now you're talking of a Z direction, which is essentially you're trying to go up, right? So when you're doing that, the speeds in that direction matter, what is known as rate of climb. Okay, so we'll be looking at deriving expressions for things like rate of climb, what is the maximum rate of climb, at what speeds, if you travel, you could achieve that, how you could redesign the aircraft, for example, the next version, to make that even better, etc. Right? So that's again something related to the speed. Now, in terms of the maximum speeds that can be achieved, we will also be looking at something called the VN diagram as we go forward, where we'll be talking about the load factor, which is essentially the accelerations that are involved compared to gravity, or gravity at the surface of the Earth, which is acceleration at 9.8 meter per second squared, as you know. So essentially, as a multiplying factor of that, positive or negative, what it can take, what the people within it can take if it's a inhabited aircraft, unlike a lot of UAVs, uninhabited aerial vehicles that we have today. Then even if you have UAVs, or for that matter, the regular passenger aircrafts or even military aircraft, apart from the human beings, there are avionics. In fact, most of the cost of an aircraft these days goes towards the avionics rather than the rest of the structure. So it's a huge percentage. And that avionics or the electronics involved also has certain limits in terms of the loads it can bear, the accelerations it can bear, both in the positive and negative directions. Otherwise, the PCBs or printed circuit boards, etc., could break apart, and you might not be achieving what you intended to with the sensors, actuators, and the feedback loops that you have between them, etc. Right? So you need to look at speeds coming from that perspective as well. So which is why, as I mentioned in the introductory email, this is a holistic topic. We will have inputs coming from the aerodynamicists, from the structures or materials person, from the controls, navigation, guidance people, and of course the propulsion term, essentially from terms of the engine that you have and how it operates, etc. So all of that will be there. So we talked about mileage, we talked about speeds. Okay, there are other speeds as well in terms of the maneuvers, the pull-ups, etc. We'll come to that later. But what else would you be typically looking at in terms of a road vehicle when you're trying to buy the characteristic? Safety, yes, very, very critical, and that's absolutely important. And in fact, there are certification agencies for automobiles. Similarly, you have certifying agencies for aircraft as well. In our country, for military aircraft, we have something called the SEMILAC, which is part of the DRDO, and you have the DGCA in the news for wrong reasons many a times. This is something that looks after the civilian aircraft in terms of certification. You have FAA in the US, etc. Right? So When you're talking about these, they are very, very particular about safety. That's in fact the first thing that you look at, especially for passenger aircraft, but even so for other aircraft, because at the end of the day, even uninhabited aerial vehicles are going to 747, etc. There are many versions of it, and depending upon the airlines that they sell to, and even the same airlines might want different versions. Some which can travel farther with a lesser payload, maybe spaced out seats, etc. And the other which can travel much smaller distances, let's say regional short haul flights, but at the same time you can take many more people. So it's kind of a these are things that from a RFP or requirements that you're trying to list out when you're designing, you need to kind of compromise on certain things. If you try to increase or better the performance of one aspect, you might have to deteriorate something else. It's all a question of the mission or the typical or primary missions which are dictating. But most aircraft these days, even in the military for that matter, for example, the Joint Strike Fighter, you need to answer a lot more people in terms of the kind of missions that you need to cater to, and therefore the design becomes even more constraining, and that's why you typically don't perform at your best in each one of those aspects, but you arrive at something that is what we call as the jack of all trades, master of none. So what we are talking about here in this course is also something like that. We want to, as flight and space mechanics engineers, become a jack of all trades. But here, at least, most of your master's students, so instead of master of none, it will be master of one at least. So you're specializing at least one or a few subjects so that you're trying to get into it. But especially if many of you are thinking of PhDs, etc., you should also think that over a long period of time, digging deep was good. In terms of research, you try to take a very narrow area of, let's say, aerodynamics or propulsion or structures or materials or controls, for that matter, navigation guidance, whichever your topic is. You try to have a very narrowly defined problem and try to dig deep and get a better understanding. But over the last couple of 100 years, especially from an aerospace perspective, at least last 50, 75 years, we have understood most of these things to a reasonable extent. So digging deep doesn't give you as much as trying to also have a breadth. So as much as depth is important, breadth is also important. Then you know where things fit into each other. Because earlier days, mostly people were working on linear models, whether it's a structures problem or aerodynamics problem, typically working on linear models. So Tom, Dick, and Harry will come up with their own models, and then you essentially put that together, and you come up with for the aircraft what it is. And you know why that works, because it's linear models. Principle of superposition is valid, but you know reality is nonlinear. So, and which means that all these nonlinear models that are there are not something that you can work in an isolated fashion, get to the solution level, and then try to put them together. Right up front, you have to start working on all these together, and which is why multidisciplinary research is what is kind of picking up. We don't want to work in silos anymore of individual groups like this. There's a lot of interaction taking place, just like it is in the actual vehicle itself, as we shall see when we go forward. Okay, so any questions so far in what we just discussed? Yeah, so it's not comprehensive, and I'm trying to ask you questions and trying to get feedback and trying to explain that. There are so many aspects which will be left out, which is more of trying to get to know you and you to get to know me, in a sense that we try to have some kind of a common ground in terms of where we are heading towards. And as we head into it, we will cover a few more things over there as well, which will be kind of add-ons to what we just qualitatively discussed now. Okay, so now, as I promised, I need to talk about the acronym that my lab stands for. C stands for composites. And many of you, even though you might not be working on structures and materials, once you're into aerospace, you'll be aware that this is something that has happened over a quite a few decades now, and safety, as you mentioned, is one of the reasons why the acceptance is not as much as it should have been by now in terms of their capabilities and what actually has been translated into reality in terms of their potential. There's a lot more which could be done, but the certifying agencies are very, very strict about testing in a physical sense, in an experimental sense, rather than simulations alone. And then many of these delay the programs, and therefore you see that not of all of the advantages that composites can give have been leveraged. But as always, the inspiration comes from Mother Nature, and for all of engineering pretty much. In fact, anything that we do, we are actually trying to do things better than what our sense organs are doing. If you look at very basic science, for example, the kind of microscopes, telescopes, etc. we use only because, first of all, we were able to see. So the ability to see means that, yes, I have a certain limitation in terms of the kind of electromagnetic spectrum that I can actually see with my eyes, the visible light, as you know, from VIBGYOR or violet to red. So you can't see the ultraviolet onwards in one direction, infrared onwards in the other direction. Similarly, sounds, you can hear 20 hertz to 20,000 hertz, right? So there are certain limitations, of course, but the fact that you can see means that you want to see things which are smaller than what you can see with your naked eye, which is why you invent the microscope. You want to see farther than what your naked eye can see, then you invent the telescope. So if you look at pretty much everything that we are looking at, the fact that we can move, we can walk, right? So which is what, unlike trees, which are in a static place, of course, they move along with the earth when the earth rotates and revolves. But with respect to the earth's surface, the fact that we can move is what enabled us to think of maybe faster ways of doing it: cycling, biking, motorbike, and then four-wheelers, and then your ship. Something naval architecture or ship, whether for military or let's say civilian purposes, something that I didn't touch upon over here, because we were comparing with the vehicle that you want to buy for your use on road, and we also talked about something that is flying both in air and space. But there are things that go on rails like trains, and there are things that go on air also, which are trying to invent and in a commercially viable way, though there have been deployments of this over a period of time, hovercraft, etc. Now coming to, you're talking of, let's say, moving in water, right? Let's say ships, boats, submarines, etc. What's the difference between that and flight mechanics or space mechanics that we are trying to deal with?
Water gives you reaction force. You can't we can stop.
Okay.
But,
okay.
We have to constantly move when we are flight.
Right.
We need to have lift, otherwise we'll just...
Right. So essentially, you're moving in a fluid, whether it is liquid or a gas. Just the fact that you have larger densities over there, and there's a buoyancy that is there, which is trying to hold you up. Whereas here, that is not going to happen unless you're a helicopter, which is hovering, flapping wing vehicle, which is hovering, just like some of the birds and insects can do it. You can hover, so you essentially stay at the same place. So there is a possibility to work around these things in air also, but it's much more difficult. The amount of energy you spend is much more compared to, for the same weight and etc., compared to what you do for the ship or submarine or whatever. Okay, so both are involving certain aspects of fluid dynamics. And the fluid being typically water, you call it hydrodynamics instead of aerodynamics. And a lot of the physics is pretty much similar, just that the values of the quantities involved, whether it's density, for example, the density of air on ground is about 1.2256 kilogram per meter cube. So for roughly, you think of it as 1 kilogram per meter cube, which, whereas, you know, the density of water is 1,000 kilograms per meter cube. So 1 is to 1,000. So you look at the huge difference. Similarly, you're talking of the pressure, you're talking of the highest pressure in the atmosphere is on the ground level. We already discussed about Mount Everest having 1/3, and typically at 12 kilometers that you fly, it's even lesser. And we look at the so-called international standard atmosphere to look at how things vary as we go to higher and higher altitudes. Both in the 0 to 12 as well as beyond for certain different classes of vehicles that you're looking at. So the pressures, on the other hand, are typically from your, simple Bernoulli's equation for whatever things that it is limited in terms of the assumptions it makes. You know that the weight is what is causing that particular pressure. So all of the height of the column of air above this, all the way up to von Karman and beyond into exosphere, etc., is essentially acting. And as you go up, further up, you're essentially that rho GH is coming down, okay? And essentially you're looking at the pressure, which is much, much lesser. Again, in the case of the water pressure, it's much larger, and therefore you're trying to deal with that, okay? So, in fact, the lower you go down, like submarines, you're going to face even higher pressure over there compared to the surface level vehicles like ships and boats, right? So, but at this end of the day, the physics, the math involved, and also the kind of quantities that you're talking about are pretty much qualitatively the same, just that the orders of magnitude differences for some of the properties of the medium in which you're traversing, whether it's air or water, whatever. A lot of experiments are done in oil or honey, etc., which are even more viscous and higher density, and therefore the kind of phenomena that are observed there are even more interesting. Of course, we're talking in very loose terms over here. We're talking of an absolute quantity like density to distinguish this, but fluid dynamics over a long period of time has established certain very, very critical ways of, or rigorous ways of distinguishing this. We have something called the Reynolds number that all of you might be aware of, essentially the ratio of the inertial forces to the viscous forces, rho VL divided by mu, or rho, if you want to absorb into the mu, into kinematic viscosity, you just have velocity into characteristic length divided by the kinematic viscosity. So now that's again something which kind of determines what needs to be taken for sure in your model and what can be neglected perhaps. For example, if Reynolds number is very high because it's inertial force divided by viscous force, the inertial forces are dominating, viscous forces are very small, relatively speaking, which means that you can deal with an inviscid model, right? Similarly, like Reynolds number, you have something called the Mach number, which is essentially the speed that we talked about, so many different kinds of speeds over there, non-dimensionalized with respect to the speed of sound at the same conditions. So which you're talking about as the Mach number, which essentially talks about compressibility, right? So in other words, you have very low Mach numbers, you deal with incompressible flow. Then, of course, a lot of people think it's very simple, but yes, it's simple in a particular way, but it complicates in another way because your incompressibility constraint has to be used, and sometimes that causes a mathematical singularity and things like that. Okay, leave that aside. Even in the case of the previous case that I mentioned, Reynolds numbers, when you're talking of very high Reynolds number, you might be happy that, you got rid of viscosity, you don't need to worry about viscous terms in the Navier-Stokes equation. And Navier, if you have gone to a regular school, and Navier, if you have gone to a convent or a high funder school, right? So similarly, Kutta and Katta, and these things are all there, but I'll be using these interchangeably because I went to all kinds of schools, right? So now coming back to what we're talking about here in terms of Mach number, Reynolds number, etc. There are rigorous ways of identifying whether something is compressible or incompressible, viscous or inviscid. And when we are happy that it's inviscid, Reynolds number is very high, which is what is the case with a lot of these passenger aircraft traveling at very high altitudes at very high speeds, and large aircraft at that. the Airbus A380, for example, you are talking of 80 meters wingspan or of that order. So essentially, you're talking of almost like a football field which is flying up there, right? So these are massive, massive structures. So your rho VL, the L will be very large, velocity will be very large, and because you're flying at 12 kilometers rarefied atmosphere, the viscosity will be fairly low, and which means the the viscous terms can be dropped off, inviscid model will be valid. But then turbulence comes in, so you can have vorticity effects, and all of those going to go further complicate in terms of how you're going to deal with unsteady flow, etc. Right? So depending, but it's important for us to make sure where all your aircraft is supposed to fly, and in terms of the atmosphere layers, what speeds it's going to be flying at, what kind of maneuvers or typical motion that it's going to undertake in each one of those heights, etc. In terms of the maneuvers, let's say the climbing, the descent, etc. And then make sure that for all of these regimes, your aircraft works fine. Okay, safety is taken care of, which means that you're essentially trying to design not for a single case. You're trying to be answerable. It's like working with those of you who are into PhD, working with more than one advisor, right? So you have many research advisors. We say too many cooks spoil the broth. Right? So essentially, you might end up with something which is not good. But of course, there are certain specific problems and certain specific students who work well even in those kinds of situations. Okay, so nothing to generalize or to be prejudiced about. So composites, as I said, is essentially to make the structure lighter. Now we want to go one level higher. Of course, composites, as I said, were inspired by Mother Nature, like wood, for example. You have your bones. All these are composites essentially, and we try to take it one step further. So just like from the eye, we went to the microscope and telescope, or for hearing sounds beyond the 20 hertz to 20,000 hertz, or for amplifying, let's say, microphones and speakers, etc. In terms of the sound levels, etc. One of the students works on acoustic black holes, so we'll come to that later. But we're talking of nature inspiring us, because nature has perfected things over millennia in terms of the evolution that has happened. Things which are really optimal, or at least near optimal for the kind of functions it's supposed to do, that's what nature has left. The rest of it has become extinct, right? So that's essentially composites over there. Now we are trying to be a little more futuristic, and we can afford to do that in an academic situation more compared to in an industry situation, unless, of course, you have a very large visionary industry where you have huge budgets to spend on your R&D as well, which quite a few companies do. But still, at the end of the day, academic research is much more farther away. We work on lower TRL problems with larger risk involved, and we are okay with many of these things failing, but at least a few might succeed. And that's where the same logic that composites bring in, we want to take to the next level. What did composites do? They combine fibers and matrices in order to get the best of both worlds, and then try to get properties which are not possible to offer by either one of them individually. Now, when we go to multifunctional, what we are trying to do is to combine different subsystems into a single system. For example, we were talking of electric vehicles. You have to take huge batteries. Okay, the specific energy that an IC engine, or even a jet engine for that matter, can provide is orders of magnitude better than what an electric vehicle's battery can actually afford. So which means you have to take huge batteries with you. Now you also have a structure, because without a structure, the aircraft itself doesn't exist. That's a very basic minimum. The body that takes the loads offers a certain level of strength, stiffness, etc. Now, if you're able to combine the battery and the structure, in other words, the structure itself doubles up as a battery. The structural members are all batteries, or in a composite, each fiber is a battery. How do you go about doing that? So in that case, you're combining multiple systems into a single system. What composites did for you is to replace metals which were having much lower specific strength, much lower specific stiffness. What that means is the strength divided by density or stiffness divided by density was very low for metals, even though their absolute strengths and stiffnesses were good, which is why we had aluminum aircraft for a very long period of time. We still use a lot of aluminum alloys for a lot of things. But then when composites came up, the strength divided by density, stiffness divided by density, etc., became very large, and therefore you were able to reduce the weight fraction of the aircraft which needed to be given to the empty weight, which is part of it is essentially the structural weight, right? So then that can be translated into fuel fraction, or it can be converted into payload fraction. So you're able to fly a longer distance A to B, or for the same A to B, you're able to take more passengers or more cargo, or you're able to, for the same passengers and the same distance, you're able to fly faster. So essentially you're making it better, faster, cheaper. That's essentially what you're, because cheaper is very important. Economics and geopolitics dictates a lot of the decisions. We as engineers fail to look at those aspects of economics and geopolitics, which can dictate a lot of things. One very simple example that I cursorily looked upon earlier was when you're flying to a country where, let's say, the fuel cost is very high, you might as well take more fuel and go so that you don't need to refuel there and come back. So sometimes exigencies like that in terms of the geopolitics and economics can dictate some of the decisions that you make over and above the actual physics and the science of the problem, okay? So keep that in mind. But essentially the multifunctionality is again an inspiration from what Mother Nature offers us. Take our own body, for example, the skin. The skin not only covers our body, but if there's a cut, then the blood comes out, clotting happens, it self-heals. There's a self-healing functionality over there. There are pores in it. So when you go into a hotter place, you sweat, and the water that comes out of it evaporates, and essentially your body is cooled. So whether it's cooling or whether it's self-healing or protection or many other aspects, all are performed by the same material, same structure. So that's essentially what we are trying to get in here as well. I just mentioned combining batteries and these structural material, but with the structural material you can probably combine electromagnetic properties, so that the same thing which functions as an antenna, etc., for example in an AVAX kind of an operation, airborne warning and control systems, you would combine the structure with that. So the aircraft itself operates as an antenna for you. So that's combining certain electromagnetic properties instead of energy storage. One very common example of multifunctional materials, many of you who are into structures or materials might know, is smart structures, where you're looking at sensing and actuation in a co-located fashion. In other words, the same entity does sensing for you, actuation for you, and is also your structure, which is load-bearing, offering strength and stiffness, which means that there's a feedback loop that is there, and therefore it can adapt to different situations. When we go to a very cold place, we can probably feel very cold and miserable for a certain period of time, but very soon our body adapts. So essentially adapting to the environment is the way to survive, okay, first of all. And then of course you want to go beyond the survival situation and actually enjoy yourself over there, then you have to be able to perform in that kind of a situation as well in whatever work that you are involved with. Same thing with the materials that go into making this. You're trying to make that multifunctional, which also means that you deal with multi-physics, sometimes multi-science. For example, in the battery, you need electrochemistry, not just physics. And then you try to look at that aspect. So C and M covered. The next thing is N. As I mentioned, almost everything in reality is nonlinear. The Earth is nonlinear in terms of its behavior. The atmosphere is, the aerodynamics, the structures, controls, etc. So same is the case with the materials that are involved in terms of how the stress versus strain varies. A lot of people know Hooke's law, which is direct proportionality, but that's valid only up to a certain point, and it's not beyond a certain point. The strain to displacement relationship, which is much more important in an aerospace structure, because we design everything very thin-walled tubes. We have thin-walled airfoil cross section. The skin is very thin compared to the chord of the wing, etc. So when you're dealing with things like that, you can have still small strains but very large displacements. So many of you have traveled on aircraft. If you just have been able to afford a window seat, you see that the tips are moving by a fairly large distance, visible when you're taking off and or landing. So you really see how much of tip deflection that is going on. So in other words, you could have very large displacements and rotations, still have small strains because of the length scales involved, because the wing span or semi-span is much larger compared to the chord and the thickness. So therefore, it's kind of a slender beam, as opposed to a beam like this that you see in civil engineering structures, where the cross section is still small compared to the length, but not the ratio is not as small. So when you have thinner and thinner structures that you're dealing with, then the displacements and rotations are going to be large, but still at the material level, the strains are going to be small. So your stress-strain relationship will still be linear. But when you're going to stretch that limit, even the stress-strain relationship will become nonlinear, etc. So that's where all kinds of nonlinearities are involved over there, and we try to model them. And the first thing we do with that is, of course, analysis. Unfortunately, that's how we, being trained in Western science right from our school, tend to look at things, unlike an Indian approach to science, which is typically holistic in nature, where we try to look at things in a combined way. If you just look at our own example of flight mechanics that we are dealing with, I said that this course is going to be in the 2/3 portion restricted to fixed wing aircraft, right? How are we able to do that? George Cayley comes in, okay? This is a guy who sees, yes, for a long period of time, people have been inspired by bird flight, not so much insect flight, but these days insect flight is the driving thing for a lot of research. But then bird flight, and you're trying to mimic that. But what were birds doing? Or for that matter, what do insects do? Essentially, they are offering two very critical forces for flight, which is the lift and the thrust, by the same motion, which is essentially a flapping motion, right? What we did when we went to the Wright brothers flight, and for pretty much the last 123 years, very significant 1, 2, 3 years, that we have since 1903, December 17th flight that the Wright brothers took, almost all the aircraft, with a few exceptions, have been fixed wing aircraft. So yes, gliders don't need engines, but apart from that, essentially you're talking about all powered flight, you have a separate engine. It could be a piston prop, it could be a IC driven prop, or it could be a jet engine, it could be a turbojet, turbofan, it could be scramjet, ramjet, whatever you have. Essentially, you're divorced the functionalities. What I was talking about here is combining the functionalities into the same thing so that you become lighter and lighter. Here, what we have done is to separate out. Of course, that has given us a lot of advantages, and also in terms of the basic understanding, etc. But it's time to revisit that and see how things. For example, we've been talking about, yes, battery is terrible in specific energy and specific power compared to your IC engines, or in terms of the fossil fuels. But what you're talking about over here is something which was not developed for a long period of time. Remember, the first automobiles which actually came up were actually electric automobiles. Then these big companies came up like Ford, GM, etc., which kind of drove in so much of money and also political sucking up to make sure that the battery or technologies or electrical technologies didn't develop as fast a rate. They didn't get enough funding as the IC engines or jet engines and others got, and which means that over the last 125 years, the amount of investment that has gone into developing those technologies was much, much more, and a lot of brilliant minds because they had to sustain their own families as well. They went working for that, and essentially you see the result of all of that. But now you see, again, after a long period of lull, battery technology is picking up, not because of electric vehicles, which has happened, of course, in the most recent years, but mostly because of laptops and mobile phones, especially the smartphones, where you're trying to do a lot more in a smaller form factor, and then you're also trying to ensure that the battery lasts long, which means that the battery technology has to improve, the cooling technologies have to improve, because battery doesn't mean just a single cell. There's so much of ecosystem that goes along with that, and all of that has to be developed, and a lot more money has been pumped in more recent years, and we are seeing the effects of that, not as fast as possibly we would all like to, but things are going to happen. It's not a question of if, but when. So that's the direction in which we are moving as far as these technologies are concerned. So that's analysis. The reason why I brought about is in the fixed wing aircraft, you have kind of separated out the propulsion functionality from the lifting functionality, and that's essentially going away from how nature typically tries to do these things, right? I mean, it's not that we have to always copy nature, but we can learn from it and adapt it intelligently to whatever problems we are trying to solve. And we can afford to be different at times, but at the same time, we have to evaluate the different options that you're taking in a design, because design is all about decision making, and many of these are going to be counterproductive one to the other. If you take one, the other suffers, etc. So you have to ensure that you come up with some kind of a golden mean between your requirements and try to do that. Whereas in analysis, by the very nature of it, you're trying to break it up into parts. You can't analyze something holistically. Of course, we are getting that capability slowly today. For example, if you want to do, let's say, leave alone aerodynamics, propulsion, controls, navigation, guidance, etc., only structural analysis. If you want to do for a full aircraft, if you want to do a finite element analysis, a full 3D finite element analysis, which is kind of rigorous and which can give you reliable results, and leave alone dynamics, is just a static test you want to do, it takes days and days, even on supercomputers, on the best of the computers that some of these companies can afford. So that's the kind of mathematical modeling complexity we have. In spite of the huge improvements we have had in computational hardware and software, operating systems, etc., we still have that lack in terms of how we are approaching that particular thing. And that's where I think we need to have a little more understanding of how we can, because if you're doing separately and each of them is nonlinear, as I already told you, principle of superposition is not valid. Each of them can give you a big kick. You can get many journal publications as well, but at the end of the day, it may not be of relevance to the industry in terms of making a decision. So essentially, you have to see, of course, both are important, just that you have to try to see that somewhere there's a practicality about it, and somewhere there is something that will actually go into a flying vehicle. Because if something that you worked on is on an actual flying vehicle today, the kind of kick that you get out of it is much, much higher than what you would get just by seeing your name on a publication. But if you are able to do both, well and good. That's the best way to approach problems. So analysis is all about breaking up into parts, and that's not limited to engineering. If you look at even the allopathic science of medicine, you see today you go to a hospital, you see a huge list of as many names as you see specializations as well, whether it's radiology, cardiology, geriatrics, obstetrics or gynecology, pediatrics, etc. It goes on and on in terms of the age, the gender, the different parts of the body that you're dealing with, etc. And at the end of the day, a general physician who's just an MBBS has a much better understanding in terms of the overall perspective, but by specializing more and more, is lost some of those overview. And then unless there are, of course, a lot of exceptions where people try to keep in touch with their overall understanding and still maintain digging deep, which is what is essential. But most cases, what happens is they're so narrow, like the horses that were used for horse carriages in earlier days, where you have something which is put up metal parts on this side so that the horse is not diverted by things that it sees on the left and the right, keeps moving in the same direction. So you tend to narrow down. Then you try to do something good for the heart and something bad happens for the head. It's no good for the human being as such, right? So that's essentially what analysis does, but that's where you start, because that's where, whether it's engineering or medicine or any other thing, the diagnosis and analysis that you do is a starting point. But if you stop there, then you have lost a great opportunity, because analysis teaches you a lot of things. And just like analysis breaks you into parts, the next thing that comes in, which we also do in our lab, design, tries to put things back. So design is all about synthesis. You try to synthesize and try to see how the different parts that we have been talking about, whether it's the wing of an aircraft which was offering you the lift, but at the same time it's giving you a collateral damage of drag. Now there is the engine which is offering you what you were looking for, which is essentially thrust, but then it's giving you something which you didn't ask for, which is pollution. It's essentially the exhaust gases that are going over there. So similarly, you're talking about structures in terms of the kind of materials that you use, the recyclability after the life cycle of the aircraft which goes, and where is it actually going into dump yards, etc., or is it being recycled? So that's again very important. Similarly with your control, guidance, navigation, whatever field you take up, you should make sure that all of these are blending with something else. And typically these are so complicated today that it's very difficult, except for home aircraft builders, to kind of do it individually. We work in teams, and there are many different expertises which come together, but unless and until you understand where something that the other person says is coming out of, some basic understanding of their field, you will not be able to understand and speak the same language, and it will not be a very productive team. So for that sake, a course like this, like flight and space mechanics, is essentially going to do what we do in our lab also from a different perspective, which is essentially the design that we are trying to look at, and where we try to, instead of breaking up into parts and looking at each individually and trying to understand it in a deeper sense, we are looking at it in a broader sense, a 30,000 feet altitude. We're trying to look at things in a holistic fashion and trying to see how each of these works together, so that the working of one or the optimization of one doesn't lead to deterioration of something else, and the overall system performance doesn't come down. At the end of the day, the most important thing is for the vehicle as a whole, whether it's an aircraft or a launch vehicle, which could be a part of a missile, or it could be a part of a launch vehicle for a satellite, or the satellite itself, etc. All these things that we are dealing with should make sense in some way that the overall performance, the overall stability, overall controllability are within the required limits for the kind of missions that we set out to design this particular vehicle for. And that cannot be achieved unless and until what you have done in the first semester in terms of the courses that you took, and now in this course trying to see some salient aspects of each one of those courses being brought together and put together, so that we understand the overall behavior of the flight vehicle, be it in space or in the atmosphere, right? Okay, before that, any questions on what we discussed so far? So don't wait for me to kind of ask this. So feel free. I want this to be as informal as possible, because knowledge really multiplies when you ask questions, because sometimes I may not have thought from that perspective, and I like to get different perspectives based on the questions, and when I answer, it may or may not be fully right, but at the same time, we tend to look at things in a different perspective, and both of our knowledge will actually increase. So which is why I keep encouraging you to ask questions. Feel free whenever you want, you just raise your hand, or without even raising your hand, you can ask your question. It's not an online class, right? Now, we work a lot with,
Sir, when you talk about analysis, why why we are not thinking towards a multidisciplinary kind of analysis at the first place, just like multifunctionality design?
A very good question. So when you're talking of multidisciplinary analysis, it could be a multidisciplinary analysis which is either theoretical, computational, or experimental, right? So now, which means that when you're doing a multidisciplinary analysis, the kind of experimental setup that you need is much, much more costlier, right? In the terms of the computational hardware and software requirements, again, it's much more, because the number of degrees of freedom that you're going to deal with, the number of equations you're going to deal with, are all going to become much larger. But this argument which I'm giving, you should have accepted if I was talking to you 30, 40 years back. Today, we are dealing with computers which are so highly capable, and multidisciplinary analysis is possible, and it's being done in certain places. In fact, some of the industries that I'm going to be talking about are already doing it. Just that, unfortunately, we have not brought it down to the class level, which is very, very important to do. Okay, because only then you get the bigger perspective. Yes, after all, being research students later on for PhD, etc., you can go deeper into one particular aspect of it and try to innovate and bring out better things for the team as a whole. But that can happen only if you understand the overall requirements of the team, and which is why you need multidisciplinary models. So one is in terms of the tools, right? Whether it's experimental tools, for example, if it's just an aerodynamic test, I can do it on a wind tunnel. But if I want to do, let's say, combine that with propulsion, etc., I need a special kind of a wind tunnel which can take that kind of temperatures, which can handle that kind of fuel flow rates, etc. Then you have to have certain non-dimensional parameters, like we discussed, Reynolds number, Mach number. Certain things associated with the thermodynamics over there, that has to be replicated. Otherwise, it may not be a meaningful translation of the learnings or takeaways to the actual flight vehicle. Because there's certain things we do on paper, certain things we do on computer, certain things we do on the lab, and certain things actually happening when it's actually flying. Okay, not everything directly translates, and you have to make sure that what are the assumptions involved in each one of them. Is it really valid when you're doing the flight? Are some of those assumptions necessary? If they are not necessary, drop it and still do it. Okay, because mathematics has developed so much as well today. Okay, the kind of mathematical models that are available, which we were not able to solve earlier, we are able to do. Still, of course, Navier-Stokes remains unsolvable for the full version. $1 million prize is there for those of you who can do it, but it will be done. It's not, again, a question of if, but again, it's when. Okay, so it's a question of that. And many times I also urge you, for example, this immediately after this class at 4 o'clock, there is a talk by Professor K.R. Srinivasan in the Mechanical Engineering Department, AR auditorium over there. He's talking about circulation. A lot of things that he'll be talking about there will be directly relevant to a lot of things that we'll be dealing with here. So if any of you are okay to go beyond these 2 hours of class and still listen to a lecture, feel free to do that. But of course, if you're more into games and sports and outdoor activities, I'd rather encourage you with that. But the reason why I'm saying that is, even if you're not an aerodynamics student, if you attend a talk like that by Professor K.R. Srinivasan talking on circulation, and then you're working, let's say, on a controls problem, you might encounter almost similar kind of equations, governing equations, just that the terms are very different. They're called by a different nomenclature. I, in fact, say that most of the new subjects that the learning is only limited by the terminology. Once you learn the new terminology of that particular subject, half the subject is learned, because at the end of the day, it's the same math and physics and science which goes into it, just that they call it by different names. And kind of what is more important, what is less important changes, and therefore what you can neglect, what you have to keep, these kinds of things changes. So when you go there and come back, so somebody might be working on something on a regular basis, and for them it's so easy, just that your way of perspective, again coming to the horse kind of analogy, you are looking at it from a particular way. You might be breaking your head on a particular problem for a year or more, but then somebody else might be doing for some other completely different scenario using similar kind of math that is involved, and then you can borrow that idea over here, and it always happens. And I'm not saying this out of the blue, because my advisor at Georgia Tech, Professor Dewey Hodges, unfortunately we lost him a few years back, but he was somebody, we had something called the brown bag lunch. Every Wednesday, you bring your own lunch in a brown bag, because that's how, if you buy lunch, that's how it's given to you in a paper bag which is brown in color. So you bring that brown bag lunch to a talk which is happening during the lunch hour, and you eat while somebody else is talking, okay, hungrily. So then the idea is that he used to attend brown bag lunches in every other department, and it was crazy to see him do that. But some of those, immediately after the talk, he will go talk to that person, and it will within a few months it will end up in a paper in which both of them are co-authors. So essentially, you're trying to borrow somebody else's approach to your own problems and then try to solve it, or vice versa. They might be stuck up with something and they might be cribbing and complaining about it in their talk. Then you say, oh, I'm doing something very similar and it works fine. Now, why don't you try this? And then they get together and they could do something great out of it, which is why be open. When you say open mind, they say it's like, don't be like in a box, but it's really not a box. There's no such boundaries over there. You can let loose and try to understand. Of course, time is always critical and you need to manage that appropriately. But if you can afford it, then be open to ideas from other disciplines, which always kind of helps, right? I hope I answered your question. Yeah, anybody else? Any question? Yeah. So we work with a lot of industries. I'll not list them all in a comprehensive manner, but let me just start off with the alphabet ABCD. So we work with the A company like Airbus. So of course, we are not far off from the B company. In fact, we work with two of them, Boeing, of course, and Bell Helicopters, which is actually part of the Textron group today. And we work with them internationally, both in India as well as in the US and Canada. And many of the problems that we work on there are not consultancy problems. See, a lot of people work on consultancy problems where you have already an existing body of knowledge which you apply to a new problem and try to solve it for them. Okay. Whereas here, along with them, you're trying to learn about something they're struggling with and try to solve that with new body of knowledge that is developed as part of the project. So that's the kind of things that we typically take up, because then you have an academic output out of that as well, in terms of, let's say, a journal publication or a conference publications, etc. And then at the same time, you're trying to solve a real life problem for the industry, which is a pain point for them, either in the short run or the long run. And for many of these, we are like long-term partners. So for example, with Airbus, I head a program called Link the Top, where we handle students from different countries. Like for example, in India, let's say IISc, in Singapore, National University of Singapore, or in the, let's say in France, we deal with ISAI, Supero. So essentially, some of the best schools for aerospace in these different countries, we bring students at different levels, PhD, masters, bachelors, etc., a group of, let's say, 20, 25 students, and make them visit each of these three countries. We take them around, and so then we expose them to the aerospace ecosystem there. For example, if you come to India, you have all these companies like Dynamatics, etc., which are like tier 2, tier 3 partners for the mainstream companies like Airbus, Boeing, etc., which make all of these parts on a regular basis, be it the wing or the tail parts, or let's say the doors, etc. So when they're doing that, a lot of people in the so-called developed countries have not seen that, because for long their countries have outsourced all of these to other countries, and there are no manufacturing facilities worth their name in many of these places, even though they might be economically very well to do. So which means that they get an exposure to that. Similarly, when we go to Singapore, for example, no big aerospace industry there, but for pretty much a lot of part of Asia, that's the MRO hub. MRO means maintenance, repair, and overhaul. Okay, so that's another aspect we as engineers don't look at, because of course there are aircraft maintenance engineers who come through a different stream, etc. Unfortunately, there's a tendency, more so in India, but it's there in every other country as well, in terms of thinking of some jobs as superior compared to something else, technicians or mechanics, etc., and look down upon them. But actually, some of the practical skills they have, there's so much for us to learn. And especially when you work in experimental projects here, you'll see some of the skilled technicians that we have. Some of them can advise you on certain problems, which maybe even your research advisor, including me, cannot probably do. So in that sense, they have a basic understanding of what works and what doesn't work, which actually we should benefit from as well. So this is one program. We've participated in a lot of their competitions and won awards, coming up first the world over. We've also done a lot of research projects like the ones that I talked about. Similarly, with Bell and Boeing also, some of the cutting edge problems in terms of the futuristic composites they want to deal with, some of the issues with composites like delamination, how to overcome that or enhance the life of the helicopter, etc. So these are the kinds of things that we typically work on. So A, B done. For C, let me give you an example of the lab that we have very close to us in Bengaluru, National Aerospace Labs, which is part of the CSIR, Council for Scientific and Industrial Research, and we work with them as well. For C, I would say the core research grants that, for example, the ANRF, which earlier used to be called the SCRB, Anusandhan National Research Foundation, they come up with a lot of announcements. So we work with the DST, we work with, we're planning to work with the DBT. It's been something that we've been exploring for some of the projects that we're looking at. Now, D, we work a lot with DRDO. Some of the things like we have done for almost 20-25 years, we've been having a close relationship. For example, some of you might be from DRDO? Yeah. ISRO? Oh, very good. Okay. So we work a lot with DRDO and ISRO as well. So DRDO labs, for example, ASL, also CPDC, etc. We've done a lot of work. For example, the Agni missile earlier used to be made with metallic pressure vessels. Conversion of that into composite pressure vessels, something that we worked on for them. And now, of course, it's been around for a long period of time. They have huge capabilities that they have developed themselves. Next, I've also been involved with a lot of academic institutions other than Georgia Tech. I get a bunch of Georgia Tech students who come and study courses with me in India, in IISc campus over the summer. This kind of, I think of as a very, very minuscule way of looking at a reverse brain drain. A lot of our students, unfortunately, for over a long period of time, and I'm guilty of that as well, going abroad to try and study. But now, because I'm no longer going to teach at many of these places where I'm a visiting professor. So they are sending their students to come here, do their regular courses with us, which I teach over here. So like that, we have students, in fact, are already here for a whole semester from IISc Course, who typically come in the fall. This is from Toulouse in France. And these people will be coming as soon as this course ends in April. From May to July, they will be here. And then I also have been doing research along with TU Delft in Netherlands, then Italy, 2 schools in Milan and Turin, etc. Right? So this is as far as a little bit about me is concerned. I'll complete that with this particular slide. So I'm a hardcore AE guy, which is what, in spite of my research being in structures and materials, I'm still very passionate. When the chair asked me to take this course this semester, I was thrilled, and he was like expecting a no, as he does from a lot of other colleagues. So, but I was like, yes, I'll do it. And so the reason, of course, is the foundation that I have had, AE degrees all through, apart from the PDF, and the only job that I've had is this particular job as faculty over here, right immediately after my PDF, which was also over here. And which essentially makes me, of course, love flight of all kinds. But I should definitely confess that my first love, because whether it was my BTech project or my MTech project or even my PhD, they were all related to helicopter rotor blades, which is why I get excited even today when I fly on a helicopter and see something new or peculiar about it. And whoever is interested, including my daughter, if I try to explain, even if they're not interested, I try to make it interesting enough to at least something they learn about it, right? So And then my lasting love, I should come to the Indian Air Force Group Captain. Can you please stand? Nanjappa, who will be one of your research and teaching assistants over here. So, as many of you would know, the Group Captain is just number 3 from the top in the Indian Air Force hierarchy, and he is working with us on flapping vehicles, okay, and not flapping as inspired by birds, but flapping as inspired by insects. If birds was a very, very difficult leap, because you go down the Reynolds number, you go down the Reynolds number even more when you go to insects, because remember, it is rho VL by mu. The velocities are even smaller for insects compared to birds. The lengths, or the characteristic length, is also much smaller for typical birds. Of course, there's a range for each category, but overall I'm saying. And then, of course, the speed, the viscosity and other things depends on the altitude at which you fly and the medium in which you fly, etc. Some might be amphibious, both in water and in air, etc. So we are trying to learn back from Mother Nature certain things we had as a species, as a Homo sapiens, we had stopped, or at least were too slow in learning over a period of time. We are trying to resurrect that and see what can be done in our lifetimes, and probably see how people can take over from there as we go forward. Okay, so this is my basic background from an academic point of view. So as I said in my email, I welcome you on board to fasten your seatbelts for takeoff, launch, orbit, and more. We've been talking about these terms earlier today, but we'll talk about it in a much more rigorous way, because, for example, we talked about the takeoff length in an airstrip, how to determine that for a typical kind of an aircraft. Then in the last third of the course, or maybe the second, depending on how I switch it, we'll be talking about launch vehicles, both for missiles and launch vehicles for satellites, and then, of course, some satellite orbits and orbital mechanics, etc., deeply influenced by the motion of the planets around the sun, about of the moon, about the earth, etc. Okay. So now, of course, you have a formal description in your scheme of instructions, but I would rather prefer this informal description of this. As you already know, I'm taking your time immediately after lunch. So as you digest your food, I hope you'll digest your food for thought here as well, right? So 2 to 4 in the same room, A105, because this is the only good room which has this interactive whiteboard, which I want to use extensively for this particular course. Today I didn't do much, but I'll probably draw a few things as we go forward, both on this whiteboard as well as over here. So as I already mentioned, there are certain peculiarities of this course, apart from the fact that it is the first course in this whole listing of aerospace. It's a 4-credit course, and it's a core course, and it's in fact the only core course that you have this semester, if I'm right? So for second semester, so all of your other core courses were done in the previous semester. So though this is for MTech students, as I already mentioned, the bachelor's, few that we have, and maybe even MTech students, most PhD students, of course, are also welcome, because they can see things from different perspectives. 2 of them are sitting right here. They had no choice. Okay. So now coming here, in terms of the description, as I already mentioned, the difference between analysis and synthesis. Analysis, breaking up. Design is essentially synthesis, bringing them back together to understand the whole thing. So in that sense, we will try to make it as absolutely holistic as possible. But language has its own limitations. So at a time, I cannot be talking about all 4 streams, but we will connect it as we go, and some classes might be a little aerodynamic dominated, especially in the first few classes, because that's something which is kind of different from, let's say, the road transport, except, of course, when you're talking of F1 racing cars, the aerodynamics that they deal with far, far superior to even any of the aerospace aerodynamics that we deal with. Okay, so we cannot generalize, but nonetheless, for most of the commercial passenger kind of road transport, we are dealing with things on a 2-dimensional surface, and so therefore we are not dealing with the 3rd dimension, in which is what requires the lift for. And so you're essentially overcoming gravity and you're trying to fly, whether it's in hover or cruise or climb or whatever. So all of that will involve a lot of these other specializations that you have gone through in the previous semester as core courses, and we'll try to see how they all fit in, right? So then, which means that we'll be jack of all trades. Okay, so we'll not be able to go into each of them deeply, even if we wish to, because we don't have that luxury of time, in spite of this being a 4-credit course. So we'll try to do a reasonable job. What is the salient features? I'll try to extract out. And for those of you who are interested, always these days, there's no limit in terms of the resources that are available, starting right from the YouTube videos to LLMs. You ask and you get to know, right, how true it is. Of course, you have to take with a pinch of salt, but for most things, it is really good and it's improving as well, which means that in the future, I might be out of job. Okay, that doesn't matter. I'll be happy. Okay, so coming to the next thing here, as I said, how many of you are from an aerospace background, BTech in aerospace? Whoa, that's good. When I taught this course in 2013, probably last, I hardly saw 2 or 3 hands. So it's just nice to see a lot of institutions teaching aerospace and many of those aerospace students coming for a master's level course. So bear with me, I'm really sorry. A lot of things that I'm going to be teaching over here will be kind of repetitious with some of the things that you have already learned as part of your undergraduate program, but it's primarily, this whole course was essentially designed for non-aerospace engineering students and also it doesn't matter whether they are masters, undergraduates as well, from a background of that to get to aerospace in terms of trying to understand the random set of courses that they did in the first semester, how they are all correlated, which is what we will try to do. So if you have a little more advanced questions, I don't mind answering them. If those with the aerospace background, if you ask me, I'd be happy to answer that either during the class or after the class as well, as far as I know. Okay, so now coming to the intent, or what we call in our typical Indian language as a sankalpa. So we say kalpa for imagination and samkalpa for a sumptuous kind of a intent that we have. And what is the intent that you're trying to do? As I already mentioned, as a debate between depth and breadth. And here we are trying to look at the breadth more than the depth, which you hopefully got to some extent in the previous class. So you begin deepening your AE routes. Now it's time to get the bigger picture at 30,000 feet. So this apostrophe is also, as you know, used as a symbol for feet. So 30,000 feet too, right? So now, what does that mean? So we want to make sure that through these lectures, and some of you, the videos of this will be posted almost the same day, if not at least the next day, which means that if you have not understood something or if you have missed a class, I don't mind. You can just go through those recordings and try to understand them as well, or understand them better. So facilitate you to do what? To self-realize. It's essentially, I think of my role, or for that matter, any teacher's role, whatever, right from kindergarten all the way to PhD or a postdoctoral mentor, our role is essentially to facilitate. At the end of the day, we can only take the horse to the water. The drinking has to be done by the horse, right? And I'm not talking of the horse like this, a free horse. Okay, so that, which is what I want you to do, self-realize and appreciate how other seemingly disconnected core courses that you took in the first semester have a role to play in each one of these. For example, if you look at the very next numbered course, this is, remember, AE 201, you are attending right now. You attended a course AE 202 before AE 201. Okay, and there's a reason for it, because you needed to have some appreciation of each of the basics of each of those fields in order to be able to do that. So essentially, when you're talking of the fluid dynamics, the main thing that comes in is the aerodynamics, because this is going to be flying in air and eventually in space as well. So which means that the main thing, we were talking of the commonalities between a vehicle that you're trying to buy for your road usage with the performance aspects of the aerospace vehicle. But there's a difference as well, which is what we said is the third dimension, it's taking off, right? Of course, there are these days there's a company which is already getting into production, commercial distribution of racing cars, flying cars. Okay, so which of course has been talked about for a long period of time, but now there's a company which is already taking orders for that, and this year, if not in the early part, at least towards the later part, they're going to actually be delivering those cars. So the kind of designs will be very different over there because it is amphibious. It has to be on the road as well as there. Not that these are not on the road. These have to taxi and take off and eventually land and taxi again to go back to their hangar or whatever. So but the amount of time they spend on this is much lesser, and the optimization you do for the longer phases of flight like cruise is much more. And if something is at crossroads between the two, you would let a little more fuel be burnt in taxiing, it's okay, or the takeoff, and still try to minimize this, because that's going to take a huge percentage of your fuel, depending on, of course, the flight. I'm talking of typically long haul flights. If it's a short haul flight, it's more like you're climbing and descending pretty much very fast. The cruise part is very slow, which means that you have to be much more careful about the climbing and the descent. And of course, you have to be careful about everything, but in terms of when the conflict arises, which do you give priority to? So that's essentially fluid dynamics, which will take care of the wings predominantly, which is what you studied over there. Next, because the amount of lift which is generated from the other surfaces, even though they are airfoil surfaces, much smaller compared to what you generate out of a wing in a typical conventional design. Of course, there are going to be different kinds of designs that we'll be talking about, where these could be combined, etc. The tail could be in the front, which is a canard, etc. So we'll talk about those peculiarities later, but most of the time we talk of a conventional aircraft like this. Showing a beluga and saying conventional is not a great thing, but hold on with me. Next time I will get a much bigger model, military model at that, thanks to the group captain, and we will probably in the last bench also you'll be able to see what I'm trying to showcase over here. So that was 202. So next should be 203, which you already finished as well, which is mechanics and thermodynamics of propulsion. We talked about these two guys, the engines, the jet engines, typically turbofan in many cases, but also turbojet, scramjet, ramjet, etc. And when we go into space, rocket engines as well, right? So that we will try to put together in this entire single body, not talking of it as parts, not as a cardiologist, radiologist, neurologist, etc., but as a general physician, right? Now, the next thing is the flight vehicle structures, which luckily another of the very few rare breed of pure aerospace guys taught for you, at least partly. Karthik Venkatraman who has an undergrad, was one of the few guys who has an undergrad degree also in aerospace like me. We had a few in the past, but many of them have retired or left. So most of the people that you have are undergrads in civil or mechanical or electrical, communication, chemical even. So nonetheless, to be fair to them, a lot of them have tried to understand the basics of many of these things and tried to piece them together. Next, 205. So that's structures. Structures, of course, you don't see over here. I need a cutout for that. So essentially what goes into it, it's the skeleton. It's like in a human body, the skeleton is the essential structural load-bearing entity. Others support it, like the skin, etc., but the predominant load is taken by that. Anything else which phases that load immediately transfers it through a series, through a chain to the skeleton. So that's essentially what goes into the, let's say, the fuselage, the wings, and all of these in terms of the ugly stuff which looks inside, which for me and those who work on structures is very beautiful. Okay, beauty is in the eyes of the beholder, as we say, right? So that structure, whether it's the spars, whether it's the ribs, or whether it is the stringers or the longerons, etc., and the skin, of course. not to forget. So all of that contribute to that mechanics of light vehicle structures. So again, a part of the general physician's diagnosis and healing, right? Next, the navigation, guidance, and control. Specifically, I didn't talk about when I said aerodynamics about this because the predominant function of the tail is stability, right? The horizontal tail and the vertical tail, it offers a certain level of stability. And that's essentially getting into your navigation, guidance, and control. In terms of the controllability, you have three control surfaces. You may not be able to see this very clearly from this demonstration over here, but next time we'll make up for it. So essentially, you have trailing edge devices on all of these lifting surfaces, be it the wings or the tails, whether it's the horizontal tail or the vertical tail. At the trailing edge, we have a leading edge in the front and the trailing edge at the rear, right? Now, at the trailing edge, you have these so-called flaps, which are essentially your aerodynamic devices, which can modify some of your lifting characteristics, like CL alpha, or which is the lift curve slope, or the maximum lift coefficient, CL max, etc. So when you want to do that, you essentially use that. But those flaps, in turn, depending upon where they are located and some kind of an asymmetry that can be generated out of them, can be used for what you see over here as part of your fifth course, which is essentially controls, right? So that control ability is actually inversely proportional, or maneuverability for that matter, is inversely proportional to the stability. The more stable an aircraft is, more difficult it is to control and very difficult for it to maneuver. So when you go to military aircraft, you will see that a little bit of instability, naughtily, is introduced to these so that they'll be able to maneuver much better. Okay, you have better control. The pilot has a better control over the bird. Now, that's as far as the controls are concerned. There are, of course, minor aspects of it, but predominantly three. Okay, because essentially control is about taking care of rotations. Okay, when you're talking of rotations, there are three primary rotations that we are talking of. If you're looking at this as a rigid body, of course, if it's an elastic body, there's a rotation happening everywhere. We'll not go into that complicated a scenario now. So this is a rigid body we are dealing with. In fact, in the first few classes later on, we'll be dealing with not even as a rigid body, but as a particle. Okay, when we talk of a particle, it has only 3 degrees of freedom, all translation in the X, Y, and Z direction. For a ground vehicle, it will just be X and Y. Now we are adding a third dimension. So even then, it's already complicated. Right now, you make it a little more complicated when you bring in the rotations. So you have a rotation like this, which many of you being aerospace background know is a pitch. So this is essentially a pitching rotation. Now, if you want to do pitch, essentially about the CG, which is, let's say, is over here in the plane of symmetry, because this is a plane of symmetry. Suppose I introduce a set of axes which are body fixed, which is X along the nose, which is in that plane of symmetry, and Z, which is downwards in the vertical plane, and Y, which is essentially along the right wing, which we call a starboard, as opposed to a port wing, which is the left. Okay, see these terminology again, we will revisit. So if you didn't listen to me or didn't register in your mind, don't worry again. Of course, you have the video to watch again, but nonetheless, even if you don't watch, we will be repeating in the future classes as well. So now, very clearly, if you want that pitching to happen, you need to generate a moment about the CG. And that moment has to be in this particular direction. Let's say you want to increase it this way, then essentially you want to apply a moment like this, which is along the positive y-axis direction. When you want to do that, how are moments generated? By forces acting far away from the CG. So that's where the horizontal tail comes in. And so now if you want to pitch nose up, you're essentially trying to use the elevator in such a way that the elevators deflect upwards so that your lift from the tail is reducing or it becomes even negative. So which means that that force about the CG is going to make it rotate about the CG. So this is essentially a pitching motion that is happening because of the deflection of a control surface called the elevators. Okay, in some aircraft, the wing and the tail are combined. Then you might have what are known as elevons, which is elevator plus the aileron. That brings us to the next control surface, which is aileron. Okay, now as I said, this whole thing is flap, and it could be used simultaneously on both sides to be deflected downwards, especially while taking off and again while landing, right? So because you want to increase the lift, essentially your CL, and therefore you make sure that both during takeoff as well as landing, you will be deflecting the flaps at the rear end, which we call as the trailing edge of both the wings. But then the outboard portions can also be deflected in a differential manner. In other words, when one is deflected upwards, the other is deflected downwards, or vice versa. So when you do that, it's very clear that whenever you deflect downwards, there is an increase in lift. Okay, and we will see why that is in terms of the aerodynamics involved later on. But take it from me now that essentially it's like almost effectively increasing your angle of attack, and essentially you're trying to increase the lift. So when you're deflecting the aileron down over here on the right wing, and deflecting it upwards on the left wing, which is the port wing, what you're doing is that you're increasing the lift here, decreasing the lift here. So essentially it rolls. Okay, so that is what is the second rotation. We already talked about pitch. We are now talking about roll, which is about the x-axis. Okay, and the pitch, remember, was about the y-axis. So we have the third axis now left, which is the z-axis. And we always, whether it's the body fixed system, earth fixed system, or any system, for commonality, we will always use what is known as a dextral triad. Okay, a dextral triad is, in other words, a right-handed system, right? So in other words, if you have the right hand thumb rule and you have unit vectors I, j, k along x, y, and z, then you're essentially saying that I cross j, which is the unit vector along x crossed with the unit vector along y axis positive, then you are essentially going to get a positive z. In this case, I am having x along this and y along this, which means that if I want to cross I cross j, the unit vector along x and y, if I want to cross them in that order, then essentially the z-axis should go positive downwards, right? Which means that the positive k direction, or the unit vector k, has to be downwards, right? So now you want a rotation about that. Now, once again, very similar to what we were talking about in the case of the pitch, but now you want the rotation to take place this way, which means you need a force this way, again far away from the CG, so that the moment arm is more. And so even if a small force is there, you're trying to get a large moment, which is going to do this for you. So that particular motion this way is called yaw, because it is happening about the z direction. So you're essentially getting the direction of turning towards the left or the right. Okay, but as we shall see when we derive the equations of motion, we will see that this rolling and this yawing, these two rotations are actually deeply coupled with each other. And in fact, they're coupled with what is known as the side drift also. Not much of a problem with aircraft, but when you go to, let's say, helicopter, etc., this is a common motion that you could have, a sideway motion as well. But here also you will have, relative to forward and vertical motion, this is very small, but sometimes you can have these drifts, especially in turbulence, depending on the direction of the wind, etc. So that can happen as well. So now that y direction translation, the x direction rotation and the z direction rotation, these three are coupled. Similarly, the other three, remember, it's a 6 degree of freedom system in a rigid body, 3 translations, 3 rotations. 3 translations because x, y, and z direction. And because you have the luxury of a plane of symmetry, these 6 sets of this set of 6 equations is getting split into 2 parts, which are independent of each other. And that's essentially your longitudinal motion happening within the plane of the symmetry. That is your x direction motion, the z direction motion, which are both are translations, and then the pitching that we talked about. So these 3 are coupled in one and the other 3 are coupled as well. So very easy to remember, because you remember the plane of symmetry and you know the axis involved in that. Along the nose is x, downwards is z. So xz is the plane of symmetry. So both the translations in that plane of symmetry and the rotation about that plane, which is essentially about y-axis, is pitch. These 3 are coupled. The other 3 are coupled, which involve 2 rotations, roll and yaw. And which is why you will see that whenever you're turning, you're not turning rigidly like this. You're actually turning like this, right? So in other words, you're yawing at the same time you're rolling as well. And this is something you as bike riders are very familiar with as well, in terms of on a road, when you're taking a sharp curve, you're essentially banking on the road, and essentially that's what helps you to stay stable, right? Because of the kind of forces that are involved when you're traversing a curve, as opposed to a rectilinear or translational motion. A lot of people call this translations as linear motion. I will try to avoid it as far as possible, unless there is some legacy thing which has come to me from the slides, because linear is somewhat confusing with the linear, non-linear that we talked about earlier. So wherever possible, you replace the word linear with rectilinear, or even better, translational, okay, so that there's no confusion about that, okay. There's nothing wrong in saying it linear, because it's along a straight line, and when you plot curves, you say a curve is linear if it's a straight line. So the terminology has come from that, but there are many other connotations to non-linear or linear, which I want to avoid by calling this translations and rotations. 3 translations and 3 rotations that are involved. So that's where so the rudder deflection, I forgot to complete that. So essentially it's the rudder deflection on the vertical tail. So when you deflect that, for example, if you deflect it towards the left, essentially you're increasing the force that is generated, aerodynamic force, which is equivalent to what is the lift over here, because this is in a different plane. So it creates that, and therefore it's essentially turning around in this direction, which is a negative yaw that it is creating, okay. But from a pilot point of view, all these are very, very kind of intuitive, how the controls that he or she operates with how the deflections take place on the overall aircraft actually behaves, so that when you're pushing it forward, essentially you're trying to move forward, backward, or left or right. So that kind of intuitiveness is built into the control stick, when in terms of the control logic that is there, whether it's a mechanical system that is linking that, which used to be the case with a lot of aircraft earlier, but over a period of time, especially for larger aircraft and high-speed aircraft, you have fly-by-wire systems which essentially are electronically transmitting that controls to the actual control surfaces, and but the overall operation is essentially the same. The in-between thing essentially changes, right? So that's the 2, 3, 4, and 5. Of course, you had a couple of other courses that you did as well, which are core courses, which also are very, very significant. In fact, the math for AE, some aspects of that will come into picture over here. But as I said in the email, I'll try to simplify the math to the extent that even the undergrads can follow, because I want to keep it at the undergrad level math. Maybe a few aspects about partial differential equations, etc., will come in, but I will explain it from the understanding of the ordinary differential equations, so that it becomes simple, because you're not perhaps going to be actually solving those equations, only trying to understand their overall structure and therefore the qualitative nature of their solutions, which means that we don't actually need to get to the nitty-gritties of the mathematics, right? And the other aspect, of course, you will learn through the experimental techniques course, which we will try to see how certain aspects of that are also coming into picture, because in terms of the instrumentation for the aircraft, what's the feedback that the pilot gets in terms of the flying conditions, the environmental conditions, and how that affects the next decision that he or she is going to make, okay? So all of these 1, 2, 3, 4, 5, 6 courses, in particular these 4 courses, which are the 4 streams in this department as well, as you know, beautifully merged together in what I call as a wonderful symphony, as they say in music. For example, what Ilayaraja does in some of the European symphony orchestras. So wonderful symphony. By the way, as Ilayaraja School of Music, which has been started at IIT Madras recently to look at the aspects of science of music and try to understand how it could be engineered better, at the same time understand the artistic, aesthetic aspects of it as well. The IIT Madras director recently announced that. So what this symphony does, it renders amazing magic of what for some time was just a dream for thousands of people, thousands of laymen, laywomen, people who are people of science, people of engineering background. They were all trying to do this, how to fly, okay? So then finally, this heavier than air was possible. Because before that, balloon flight was possible. Many of you are familiar, Makara Sankranti is coming, kite flying is very, very popular. So designing those paper airplanes, competitions for paper airplanes, how far you can go with it, etc. But here you're talking of overall density of that volume. So let's say I put this into a beaker of water. I see how much of water is displaced. From that, I calculate the volume of this you're talking about. Then you know the weight, gross takeoff weight of this. So you divide the weight divided by that volume, you get the average density of this particular aircraft, which will be, I assure you, for pretty much every aircraft that you look at, is much, much larger than 1.2256 kilogram per meter cube, which is the density of air at the mean sea level. So that's something magic, like how it really happens, how something is kind of counterintuitive. Anything which light has to go up, like for example, when you heat up air, the hot air rises up. Why? Because the molecules are trying to go farther apart, which means the density is becoming lesser, which means the mass per unit volume, the same control volume that you take, is becoming lesser, and essentially it's going up. And that was what hot air balloons were doing on a regular basis, or for that matter, hydrogen balloons, helium balloons, etc. Of course, there were some disasters as well associated with that, like the Hindenburg disaster, which happened with hydrogen. But hydrogen is making a huge comeback. Like we're talking about electric propulsion, we're talking about hydrogen-based propulsion as well today, and better safety aspects are in place today in terms of the storage tanks, etc. And therefore, that's something which seems to be promising as well. And make this flight therefore a distinct possibility. I'll just go through one more slide. So, and distinct possibility, this flight, I want to make it distinct for and a possibility only for, not only for yourself to enjoy, but also more importantly to get amply inspired and eventually and innovatively try to take this to the next step. Okay, what you learned were the basics in the previous semester. Now you're trying to understand how to put it all together, but put it all together for what? Okay, so when you're cooking a meal, you come up with many ingredients and then you put it all together. Eventually you have to eat, and eating alone is not as much fun as sharing it with your friends, and that's essentially what you want to do. And in doing that, we will use not only the conventional tools and also the latest versions of that, but also we'll give an idea of the upcoming tools, including AI, ML, robotics, in terms of the design as well as the manufacturing aspects. And then maybe in the operation also, autopilots have been around for a long period of time. Fully autonomous flight, again, is something which is understood in different ways by different people, but it's something that we are moving towards as well, like self-driving cars. If that is possible on chaotic roads like in Los Angeles or New York or Indian roads, then obviously why not flying vehicles, okay? So they have been, in fact, doing it to a large extent for a long period of time. Okay, many people say that pilots on commercial flights are more for the assurance of the passengers rather than for any real motion. That's of course oversimplifying it, but essentially that's the direction in which we are heading towards. So we want to design. When we are designing, obviously there are certain things already there, which luxury the Wright brothers didn't have. They started off afresh. Of course, there are a lot of failed attempts, and you learn from your failures as well, as Edison would say. But here you're talking about already existing flight worthy aircraft which are still flying, many of them designed long back, for some designed 40, 50 years back, and many of them retired, but retired very gracefully, be it the Concorde or A380, which has stopped production, but is still flying with a lot of the airlines that it was supplied to, especially Emirates, etc. So now, but when you want to go to the next level, and which is a very, very long cycle in the aerospace industry, quite unfortunately for many of us who would like to work on, look at new projects, etc., because this involves such a huge budget, and in terms of the market studies and whether there's a real need for it. Yes, there is a need, but can't the existing aircraft do it? How much better can we get with the current body of knowledge compared to when those were designed, etc.? All these arguments come in, and as I said, a lot of the geopolitics and economics plays a role in these decision making processes, right? So, but whenever we want to design, we want to make things better, faster, or cheaper, right? So essentially newer, better performing in the various performance parameters that we discussed earlier, or something that is becoming more and more critical today should have been long back in terms of lesser fuel consumption, or to go to technologies entirely without fossil fuels. But of course, if it's an electric flying vehicle, how you're going to generate that electricity is always a debate as well. If you're still using coal in thermoelectric projects to generate your electricity to charge your batteries, then or somewhere you're just transferring the pollution source from one end to the other end. But as long as the entire ecosystem develops for that, yes, that's the right direction to move in terms of more efficient flying vehicles, because we remember, like most other engineering fields, which leave a literal footprint on the ground, on Mother Earth, we don't. As aerospace engineers, we fly in the sky, right? So whether it's in space or in the atmosphere, we don't leave footprints, but do the vehicles that we are dealing with leave huge footprints? And that's where I think we have all a responsibility to contribute towards as designers, right? With additional and or improved capabilities, softer on the environment as well as the economy, because a lot of this is economically decided in terms of the marketability eventually. For example, A380, which came up as a competition to the jumbo jet, which is the Boeing 747, could sell only about, I'm not sure of the exact numbers, but about 250 aircraft or so, 120 of them to Emirates. But the jumbo jet, on the other hand, sold thousands because it was a monopoly. Now it's a duopoly, and there's a competition. And also in terms of what is actually required for the market, because here you have two levels of the passenger seats, and of course there are different seating configurations, but you can go to a maximum of 800 plus, maybe 850 or so number of passengers. How efficient is it for the airlines to operate something like that? Are you going to get 850 passengers at a time to fly from point A to point B? Which routes should it be implemented on, etc.? So those become very, very critical decisions, and therefore, and also the timing, when a particular aircraft you begin to design and when it actually comes out to the market. When you began, maybe it was a great market for that particular kind of range or for that kind of payload, but when it actually comes out, it may no longer be. So all these things have to be accounted for in the aspect. So don't look down upon something as a non-engineering aspect. You have to look at, when you're saying holistically, it's not only from an engineering perspective, aerodynamics, controls, structures, and thermodynamics, but also from the perspective of non-engineering, non-science so-called aspects. Of course, many of these are getting clubbed into what is known as social science or political science or economic science, etc. Many of my IIT BTech classmates are working in financial companies, working with much more complicated mathematical models than what I see in a lot of my work. So it's essentially putting your knowledge to work in a different place, but at the end of the day, we have to have an understanding of everything, especially when you're dealing with something as complicated as aerospace design. Okay, I'll just complete with a couple of things on this slide. So this, as I said, is open to undergrads and to PhDs as well. So interested in grasping the basics of physics of flight, both in terms of the planetary atmosphere, though for a lot of examples will be concentrating on the Earth's atmosphere. This is something that is of interest to us as we go forward. You're talking of Mars inhabitation or lunar inhabitation, etc., at least for short periods of time. You're essentially talking of the atmospheres there to have a better understanding of that and designing the space suits for that, the kind of pressure levels, temperature levels, the composition. Like here we have almost pretty much 99.9% you have nitrogen and oxygen. The rest is very, very small. Even though we talk so much about carbon dioxide, it's all comes within that last 1%, and maybe you have more argon than carbon dioxide in the atmosphere at the surface level. And of course, it gets more and more rarefied. You said, as we saw already at Mount Everest level, it's 1/3, even lower at where we typically fly commercial flights, 12 kilometers. So you're essentially talking about something which can probably be valid in rarefied atmospheres also, the learnings from what we are doing on the Earth's atmosphere. Then there are even denser atmospheres, okay? So atmospheres are much, much denser than the one on Earth, like say Venus, for example. So then how do you deal with those kinds of things as well? So planetary atmospheres and or the interplanetary space in between them, rarefied, the ions that are involved, the electromagnetic radiations, how you deal with them. In terms of sometimes the disadvantage there is in terms of the cooling systems, whereas when you have air, you have the luxury of a huge sink, which is the atmosphere into which you can let out the heat, right? But then where you let out the heat over there when you're in vacuum, right? So, and then of course re-entry, much more complicated problem over there. We will deal with some of those aspects as well. So employing, as I said, mostly high school level math, but at the same time some bit of the bachelor level calculus and the math course that you've done last semester might come in handy as well, because the person I think who taught you is Owen Ramesh. Yeah, so he is one of the others who teaches this course. So I'm sure he would have taught a little bit of math, which is required for me, make my job a little easier and yours too. Okay, thank you very much. And this we conclude. If you have any questions, either you can ask in the open class or you come to the dais and ask me. Yeah, thank you.